All right, so last Friday, actually, different thing. Test is on Wednesday. Last Friday, we talked about band pass and band stop filters. So today we're going to talk about second order high pass, low pass, and be done. So our second order low pass filter is just a series RLC circuit where the voltage drop is taken across our capacitor. So something like this. Here's R, J omega L. One over J omega C. Here's V in. Here's V out. Once again, it's just a simple voltage divider circuit.
Sorry.
Mute yourself. So our transfer function is going to look like 1 over J omega C divided by R plus J omega L plus 1 over J omega C. Multiplying through by J omega C over J omega C. That's going to give us a 1 in the numerator. And then I'm going to have a 1 as a real part. I'm going to have a J squared times omega squared LC. Since J squared is equal to -1, that's going to look like 1 minus omega squared LC. And then my imaginary part of my denominator is going to look like J omega RC. So to make this into, or to break this down into its real and imaginary parts, I'm going to multiply by the complex conjugate of the denominator over the complex conjugate of the denominator, like I've done over and over again. So that's going to look like 1 over 1 minus omega squared LC plus J omega RC times 1 minus omega squared LC minus J omega RC 1 minus omega squared LC minus J omega RC. And this should come out to have a real part that is 1 minus omega squared LC over 1 minus omega squared LC quantity squared plus omega RC quantity squared. And our imaginary part should be negative J times omega RC over that same denominator. So our magnitude response, once again, is just found by squaring the real part, squaring the imaginary part, adding those results together, and taking the square root of the whole thing. So that's going to look like 1 minus omega squared LC divided by 1 minus omega squared LC plus omega RC quantity squared. Square this whole thing. And then omega RC over that same denominator. Sorry, there should have been a squared right there. My apologies. And this is one of the easier ones, right? So we're squaring the numerator and then we're for each part. So I'm just going to have what winds up being 1 minus omega squared LC squared plus omega RC squared in the numerator. And that exact same thing in the denominator, except the whole damn thing squared, right? So this winds up just looking like 1 over the square root of 1 minus omega squared LC plus omega RC. Both of these are squared and both of them are under the square root sign. All right, so for very low frequencies, we wind up getting the square 1 over the square root of 1, which is 1. So we pass low frequency signals. For very high frequencies, I've already told you it's a low pass filter, but this is going to look like 1 over the square root of infinity to the 4th power. So that's going to look like 1 over infinity squared, which is 0. So we pass low signals, reject high frequency signals. Because this is a second order filter, it is going to have a resonant frequency. So omega naught will still be the square root of 1 over LC, but this resonant frequency doesn't really have any particular meaning other than the fact that it is the frequency at which the impedance looks purely real. So when we had our bandpass filters and we had our band stop filters, our resonant frequency was the middle point between omega low and omega high. Now we effectively are going to have omega low, it's just going to be twice as strong. So what I mean by that is when we looked at our first order filter, we saw that it decayed at a rate of 20 decibels per decade for our low pass filter. Now we should actually see it decaying at a rate of 40 decibels per decade because we have a second order filter. So it's going to roll off much, much faster, okay? Our corner frequency, which I'm going to say is omega C, is this guy right here. And I'm going to give you a fair warning that this is an ugly relationship. So square root of R squared C quantity squared minus 4 R squared LC plus 8L squared, all divided by 2 L squared C quantity squared minus 1/2 R squared C minus L divided by L squared C. And then we wind up taking the square root of that whole big ugly thing. So this is our minus 3 dB cutoff. And our phase response will be the inverse tangent of negative omega RC over 1 minus omega squared LC. And I have in my notes here in a different color, so I'm not 100% sure this is correct, but we'll see it in just a moment, minus 180 degrees. So I believe the reason why I put the minus 180 degrees thing here is for very low frequencies, we should expect to see roughly no phase change in our signal. At very high frequencies, however, I think we're going to wind up settling to minus 180 degrees because we have a second order filter. So let's just simulate something here and double check some points. Where is my mouse cursor? There we go. So let's just make this wildly straightforward and make everything have a component value of 1. Here's my capacitor over here. 1. Need a voltage source right here. AC amplitude of 1. Missed. Here is my output node. So simulate decade, 1,000 points per decade. Let's start it at microhertz. Let's end it at kilohertz. So let me change this color from green to blue so you guys can see it a little bit better. So largely this looks exactly like what we would expect for a low pass filter, right? Notice, however, that there is a little bit of a hiccup going on here, okay? So if I were to zoom in the area between, let's say, 100 millihertz or so and 1 hertz, let's just put this from 10 milli to 1 hertz. A second order pass filter. So it might be a little bit hard to see, but in this region, so like notice over here, it's nice and flat. And then we actually see a small increase. It's not huge, maybe half a decibel or so, probably. We can find out in just a moment. But there is a slight increase before it starts to roll off. That's actually why the cutoff frequency has that big, terribly long equation, because the cutoff frequency is 3 decibels from the maximum value. Our maximum value is no longer just 1. So near resonance, we are going to see that little blurb where it gets a little bit higher. If we were to change our component values, we could make that peak more and more stiff by affecting what we talked about on last class meeting, the quality factor of our filter. So it could come up sharp peak and then roll off and all of that kind of stuff. We're just playing around with the different numbers, okay? So with this relatively low quality factor, just by looking at the thing, let's see here what our peak value looks like, right? So way over here, we're on the order of milladecibels. Getting out here, a little over 1 decibel, 1.2 decibels. So it looks like about a quarter of a dB is the amount of gain that we wind up applying to this thing. So it's very, very small, right? And then it rolls off. Let me zoom back out because I want to show you guys something else. So I think I did this from 1 micro to 1 kilo earlier. And where is my thing? Here we go. So let's say right here where we're at 1 hertz, or as close to it as possible, right? So at 1 hertz on cursor 2, our magnitude, oops, it's drifting for some reason. Our magnitude is negative 31.9 dB. Over here at 10 hertz, our magnitude is negative 72 dB. So while it does look roughly the same, we are actually rolling off at that 40 decibels per decade instead of 20 decibels per decade. So we see that we transition from the pass band into the stop band much more quickly once we go beyond that little uptick in the system's response. Okay. So it's a better low pass filter in as much as signals beyond its frequency, the cutoff frequency, get cut off more quickly. However, we accidentally see a little bit of amplification around the cutoff frequency, which might not be great. Toby.
Amplification increase with higher order.
Yes. But it also depends on the component values, right? So putting ones for everything made it very, very shallow. If we were to use different component values to increase the quality factor effectively, it would get much more steep before it rolls off. And that's something we'll talk a whole heck of a lot about in circuits 3, particularly when we're looking at Butterworth filters and all of that kind of good stuff. Because there we're effectively managing bandwidth and quality factor to try to get the optimal setup. Isaiah.
So the 3 decibel cutoff frequency. Since your maximum is at like 1.25, would your 3 decibel cutoff be at negative 1.25, or would it be all the way down to negative?
So over here, right, where we're at effectively 0 dB, up here is our peak of around 1.25 dB. So whatever 1.25 minus 3 is, which seems to be like negative 1.75, that's our minus 3 dB cutoff frequency because it's measured from the maximum value, right? So on our first order filters and our band pass filters and our band stop filters, where everything was rolling off like it was a first order thing, so everything was rolling off at negative 20 decibels per decade, we didn't really have to worry about anything like that because our maximum value was always 0 dB or 1, right? Here, because we have that uptick, that's what's skewing things a little bit and why our minus 3 dB frequency isn't something that looks like we've seen it before. All right. Looking at our phase response here as well, I can see that, like I said, for low frequencies, my filter, the phase angle should be effectively 0. At exactly our 3 dB, it should be negative 90 degrees, which would be one way for us to find it here. I think it should be minus 90. That might be the resonant frequency, is it'll be at minus 90. And then it settles down to minus 180 as we go beyond, which is exactly what I would expect. So if we were to put in numbers here, just let me grab a calculator. So if I do the inverse tangent of let's say -1 divided by 10,000. Oops, I forgot to do the inverse tangent. I get -5.7295 blah 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 times 10 to the -3. So something that's very, very small, close to zero, effectively. That minus 180 degrees there on the outside is what's forcing it to roll off to negative 180 degrees. So if we did something at a very low frequency here, so let's say omega is equal to 0, that's going to look like the inverse tangent of just 0. Which is still says it's 0. Anyway, we effectively we need to correct because it's going to be above and go down to 0 if we don't do that. All right, so the last one that I want to talk to you guys about is our second order high pass filter. So now, exact same thing that we just did, except, yes, Kate.
Previous example, what is the phase angle being 0 versus -180?
So if the phase angle is 0 of the phase response, that means that your output signal is exactly in phase with your input signal. If your phase angle is -180, which is the same thing as +180, it means that your output signal has changed polarity with respect to your input signal. So 180 degrees out of phase literally just means a sign change. That's it. So now our output is exactly out of phase with our input. So think about it from a perspective of like a sinusoidal function, okay? So let's say that we have a cosine function. 90 degrees out of phase means that we have a sine function. 180 degrees out of phase means that we have a negative cosine function. 270 degrees out of phase means we have a negative sine function, and 360 degrees out of phase brings us back around to our original cosine signal. That's it. So it's just delaying it in time by some amount that makes it look like a sine function as opposed to a cosine function. If it's a plus or minus 90 degree phase shift, and 180 degree phase shift literally just means it changed the sign. All right. Second order high pass filters. So for our second order high pass filter, this is just going to be a series RLC circuit. What do you think I'm taking the voltage drop over this time? It's the only thing I haven't taken the voltage drop over yet. The inductor, right? Okay. So here's R. Here's 1 over j omega c. That does not look like an inductor. It looks like a resistor. My apologies. That should be V in, not V out. I'm losing my mind. Here's V out. All right. So, and let me make that L more crisp so it doesn't look like a garbage C. Okay, so voltage divider rules still apply here. So our transfer function is going to be j omega L divided by R plus j omega L plus 1 over j omega C, multiplying through by j omega C over j omega C. Actually, it looks like what I did, and then we explicitly put this here because it's slightly different than everything I've done. To get rid of a negative sign, I multiplied by a negative j omega C over negative j omega C. I just didn't want to have a negative number in the numerator. So that's going to give me omega squared LC up here. And then I'll have omega squared LC minus 1 minus j omega RC. So looks pretty darn similar to what we saw for our low pass filter, except that we've got a sign change, and instead of having 1 in the numerator, we've got this omega squared LC. Breaking this down into its real and imaginary parts, I'm going to take my response and multiply it by the complex conjugate of the denominator over the complex conjugate of the denominator. And in doing so, I wind up getting omega squared LC times omega squared LC minus 1 divided by omega squared LC minus 1 squared plus omega RC quantity squared. Yes. Sorry, thank you, Isaiah. Those should be positive. Thank you for that. Just total brain fart. Losing my mind. Then we're gonna have J omega squared LC omega RC over omega squared LC minus 1 quantity squared plus omega RC quantity squared. Our magnitude response is then given by the square root of omega squared LC times omega squared LC minus 1 over omega squared LC minus 1 squared plus omega RC squared, close the bracket, square the whole thing. Omega squared LC omega RC omega squared LC minus 1 squared plus omega RC squared, square outside of the bracket, everything under the square root sign. And this looked like omega squared LC quantity squared times omega squared LC minus 1 squared plus omega RC squared divided by omega squared LC minus 1 squared plus omega RC squared, square that whole thing. This guy gets rid of one of those powers, And we are left with omega squared, sorry, right thing, LC over the square root of omega squared LC minus 1 quantity squared plus omega RC quantity squared. At low frequencies, this looks like 0. At high frequencies, this looks like 1. Because it's a high pass filter. Once again, we have a resonant frequency, omega naught is square root of 1 over LC. Our cutoff frequency is literally going to be the exact same thing that it was for our low pass filter. So square root of R squared C quantity squared minus 4 R squared LC plus 8L squared all over twice L squared C quantity squared. All that bit is underneath the square root sign plus 1/2 R squared C minus L over L squared C, the 1/2 power. And finally, our phase response looks like the inverse tangent of omega RC over omega squared LC minus 1. All right, we're done with filters. So let's talk about your test. Steady state sinusoidal circuit analysis. I'm going to put literally one problem on the exam that having anything to do with filters. It will be considered a bonus problem, meaning your in-class portion of the exam will be steady state sinusoidal circuit analysis capable of being done on your good old TI-36X, Casio 115, Casio 991, and HP 33S for you weirdos that believe HP calculators are a thing that should exist. The one problem that will have literally anything to do with filters, I will literally just ask you to give me the basic transfer function thing. So effectively, can you apply a voltage divider-like relationship to a simple network? If the answer is yes, congratulations on your 5 points. That's it. All of the stuff that I intend you to use the filter relationships for will be the design project, okay? So that's where all of this stuff is going to come into play. Expect a first order low pass filter problem, a first order high pass filter problem, a band pass filter problem, and a band stop filter problem. I wanted you to understand or have the relationships for second order filters. But as you can see, the math gets gross. And so making you design towards that would just be too much time. I don't know what you have to deal with it. Okay. So one of the problems on your so that's just your design problem. For the take-home portion of your exam, it will just be steady state sinusoidal circuit analysis type stuff that requires the use of a computer. So multi-frequency circuit kind of thing, maybe a big ugly circuit where you have to do nodal or mesh, that kind of deal. All right, what else do we need to talk about for the demo? Homework 14, problem 4. Let's see how much of a dick I was. Yep.
Is that filter problem gonna be like something that we need to derive the relationship for?
Good Lord, no.
Like the option thing, where we just have to take their
Oh, so for the take home, or excuse me, the in-class portion, you are going to have to derive it. So it's probably, I'm not going to say 100% it's going to be this, but it's going to be something like this. Here's something, it's a resistor, a capacitor, or an inductor. Here's something. Here's something. VN versus, or V out versus VN. I'm not looking for a bunch of simplification or anything like that. Just literally, can you apply the voltage divider bit correctly? If you choose to simplify it, that's great. I'm not expecting it.
Not the magnet.
No, it's literally just give me the transfer function, the first part. It's a bonus problem. I want it to be very easy. Some of you need it. All right. Homework 14. Oh, stupid mouse.
I have a question.
Yep.
Okay, so basically bar H of theta, then it's. You know, the magnitude of that.
H without absolute value signs is the transfer function. What I am expecting you to be able to do is this part that I just circled in red. Apply the voltage divider relationship. Done. Oh my God. You're gonna give me a panic attack, Walker. Where the hell is my other mouse? Because this one's pissing me off.
Say we wanted that recalculate. So we forgot what to do without
Sure. Where did I lose my mouse at? Well, now I'm about to have another one of those mouses as soon as I can find it. Open the folder, stop trying to rename it, you piece of shit. Homework 14, you said, right? That is for a wildly different class. Hold on, let me close that out. This is Circuits 1 crap. Okay, killed it. This is easy. Good. So we'll go to a different page here. So over here on the left is my transformer, which is just a voltage source. Then I have my transmission line impedance, which I'm going to call ZW. The impedance of a section of wire. That is, follow that open, need open. Then I have a load, which I'm told consumes 125 kilowatts at a power factor of 0.75 lagging. So let me write that in. I'm also told that the voltage drop across my load is 480 angle 0 degrees volts RMS or something like that. Let me double check. Yep. And I want to know, let's see, so ZW is 0.1 plus J 0.2. And I want to know what size of the capacitor I need if I want my new power factor for my transformer to 0.975 lagging. Okay. So first thing I'm going to do is I'm going to figure out the complex power absorbed by my load, right? So S load is going to be the average power absorbed by my load divided by the power factor at which my load is operating with an angle of the inverse cosine of the power factor at which my load is operating. Just as a heads up, all of that stuff right there comes from this relationship. Power factor is equal to P over apparent power is equal to cosine theta S. Just rearranging that relationship. Okay. So once I know the complex power absorbed by my load, I can then find the current that's flowing down my transmission line, right? So I'm going to call that current IW, like so, okay? So I would have S load, which I just found a moment ago, is equal to VL times IW conjugate, which means IW is equal to S load divided by VL conjugate the fraction. From there, the complex power absorbed by my transmission line is just going to be the magnitude of IW squared times ZW. And the complex power supplied by my voltage source is then just S load plus SW. This information will give me P old, and it will wind up giving me theta old. Yes. Why can't I add the powers together? So there's a thing, and I believe it was covered in circuits 1, called Teligent's theorem. Teligent's theorem effectively says that power supplied has to equal power absorbed. So if I have a source that's supplying power to a system, it has to, the total power absorbed in the system has to equal the power supplied in the system. If it doesn't, then the law of conservation of energy has been violated. Yep. So, all right, so there's P old and there's theta old. Theta new comes from our power factor new. So I need omega, which I tell you that F is 60 hertz. So the last thing I need is the voltage drop across my capacitor. So the voltage drop across my capacitor is going to be whatever VS is, which we weren't told. So VS should be IW ZW plus, excuse me, that should be VL, not ZL. That's one way to do it. or VS is going to be S VS divided by IW conjugate. Either way gives you the exact same number. Now you have all of the parts to put into the equation to calculate C. Do that. Hojun, you've got your hand up. What's up? Yeah, I'm done with this one. Can I do it? Absolutely. Will I do it? Probably not, but I will tell you what could work. Determine the average power supplied by this dependent source. So it's a multi-frequency circuit, so you're going to have to do superposition and all of that kind of good stuff. And yeah, all right. So let's say VS on and CS off. Okay. So let's see. So the voltage source is 5 times 10 to the 4. So let me see here. So omega is 5 times 10 to the 4 times 1 millihenry. So that's looking like a J50. IC. I have goldfish brain today. I cannot remember literally anything. I'm going to close this because it's just pissing me off at this point. Arrows to the right. Down here, I have a capacitor. I'll figure that out in a moment. BS is going to look like 18 angle 0. Nope, 18 angle negative 90, excuse me. See that capacitor. So I have 1 over 5 times 10 to the 4 times 1 times 10 to the minus 6. That's going to look like minus J20. All right, let me think. What are we realistically looking for? I want power absorbed or supplied. Power supplied. So I want the current flowing into the negative polarity terminal. So that's going to be this voltage VDEP like so. I'm going to be lazy. let's call this phasor current I1. And this phasor current I2. So we can see from the jump here that 3 IC is equal to I1. Now I don't have to do KVL around the top loop, or I'm going to have to in a moment because of figuring out what VDEP is. Also, I forgot to put plus sign there. KVL around my bottom loop thingy is going to look like minus J20 I2 plus 5 ohms I2 minus I1 plus 18 angle negative 90 degrees volts is equal to 0. And this is a separate equation. VDEP is going to look like 5 ohms I1 minus I2 plus 10 plus J50 ohms I1. And just for the sake of argument, because we'll need this, IC is going to be negative I2. So that's all of our analysis crap going on for the voltage source on and the current source off. Okay, so we can solve for all of those quantities by using a computer and those 4 equations. Now we would analyze the circuit with the voltage source off. What the hell just happened? And the current source on. So it's going to look something like this. All right, so let's pop back over here. 6 angle 0. Ten and 5. Let's see, so my frequency is half as large. So my impedance of my inductor should be half as large, and the impedance of my capacitor should be twice as large. So that's going to look like J25 and minus J40 if my mental math stuff is working right. Anybody got beef with this? Okay. I'm going to do mesh again. Nodal could definitely work. So let me think. So I'd have 1, 2. Right. Yeah, we'll do mesh, or excuse me, we'll do nodal just for shits and giggles. It is supposed to be on the left, excuse me, on the right like it was earlier. Thank you for that, Isaiah. Because we want the current flowing into the negative polarity terminal for supplied power. So thank you for that. All right, so somebody suggested nodal, so let's do nodal. I'm going to call this V1. I'm going to call this V2. So, KCL at node 1 is going to look like 3IC minus 6 angle 0 degrees amps plus V1 minus V2 over 10 plus J25. KCL at node 2 is going to look like V2 minus V1 over 10 plus J25 plus V2 over minus J40 plus V2 over 5. IC is just V2 over minus J40. V dep is just negative V1. Solve, solve, solve. Hojun. I don't see any source transformations or anything like that that we could do to make this easier. So I think it's just going to need a computer. Isaiah, what up? Yeah. So from here, what I would do actually, so let's go up here, right? So I'm going to call this P1, okay? And that is going to be 1/2 the magnitude of V dep times the magnitude of 3IC times the cosine of the angle of V dep minus the angle of 3IC. That's giving me my average power for this guy at this particular frequency. Here, P2 is going to be effectively the exact same equation. 1/2 times the magnitude of V dep times the magnitude of 3IC cosine theta V dep minus theta 3IC. And then our average power overall is just going to be P1 plus P2. Now, I do want to make a point here. Generally speaking, superposition isn't great for calculating powers. However, in an AC system, it's an okay way to calculate the average power because all of the average values of the cross frequency terms wind up going away when you integrate over the integer number of periods involved, right? Which is something that I showed you guys when we were looking at instantaneous power in multi-frequency circuits. The average power is just the DC part, and that's literally going to be just these relationships. So you don't need to waste the time finding the instantaneous power and then only finding the DC parts. We know all of the AC bits aren't going to contribute anything. So I think that's a reasonably okay way to look at it. I'm hesitant to say it's a good way to look at it. So like in a DC circuit, power is not related to, or power is not a linear quantity because it's related to voltage squared and current squared, which is why we couldn't do it. But here in the AC circuit, right, realistically, if we instantaneous power, we would find the voltage as a function of time. And so it would have a term at one frequency and a term at another frequency. And then we would find the current as a function of time, and it would also have two different frequency components. And then we wind up expanding that whole thing out, right? Which is exactly what we did in the lecture on power, instantaneous power in multi-frequency circuits. Because we're only interested in the average power, that's just the DC portion of that thing, which is only going to have this part, oops, and this part. All of the other parts are sinusoidally varying, and their average value is going to be 0. So it happens to work in AC circuits because of how multiplying sine functions work. And then the average value of a sine function over an integer number of periods is always 0. It can still work. So let me do this just really quickly. Right? So I have a voltage V of t that is, let's call it V1 cosine omega 1t plus V2 cosine, actually I need a phase angle in there, theta V1 plus V2 cosine omega 2t plus theta V2. And we also have a restriction here that omega 2 in our example is just twice omega 1. So the angular frequencies need to be related to each other in some way. Integer is best, just so that when we do the integration, it's obvious that things will cancel out to 0. Okay. Then I have a current I of t is equal to I1 cosine omega 1t plus theta I1 plus I2 cosine omega 2t plus theta I2, right? So my instantaneous power is going to look like 1/2 V1 I1 cosine theta V1 minus theta I1 plus 1/2 V1 I1 cosine 2 omega 1t plus twice theta V1. No, that's not right. Theta V1 plus theta I1. That's what I got for multiplying this guy right here by this guy right here. And now I have to do all that cross multiplication crap 3 times. This part right here that I underline in pink is a DC term, okay? It exists only because I'm multiplying an omega 1 thing by omega 1 thing, right? When I multiply this guy by this guy, I'm going to get a similar expression to this, where it's going to have a DC term and then an AC term. When I multiply anything underlined by red by anything underlined by blue, I'm only going to get AC terms. The average value of the AC terms is always going to be 0 if omega 1 and omega 2 are related by an integer multiple of each other. So that's why I can add the DC terms together and just get the average power. So let me show you what I mean by that specifically, right? So let me do the second part here. So I'm going to have 1/2 V1 times I2. Now I have to take the difference of those angles. So that's going to look like omega 1 minus omega 2. T plus theta V1 minus theta I2. And then I'm going to have 1/2 V1 I2 cosine omega 1 plus omega 2 T plus theta V1 plus theta I2. See how both of those are fully AC terms. The omega parts did not go away, so they're sinusoidally oscillating. Right? Yes. Because they have to be periodic. Right? Because the average value of a function, so x average is 1 over t times the integral from 0 to t of x of t dt, where x of t is a periodic function. If my angular frequencies weren't related to each other, so like let's say that it was an irrational relationship. So let's say that signal 1 had omega 1 was equal to 2 radians per second, and omega 2 were pi radians per second. I'm not going to get a periodic function. It's literally impossible to get a periodic function. Right? So they have to be some combination of frequencies such that there is a period I can integrate over. And the average value of a sinusoid integrated over an integer number of periods is always 0. I'm not going to give you anything you can't use this trick with. Yeah. You'll learn more about checking for periodicity and all of that kind of stuff when you get into your linear systems and signals course, because that's one of the things that you explicitly have to check for to be able to do certain mathematical operations. Troy. I don't remember. I'll look at my results. I don't know. Yes. Yeah. I guess, yeah. Is that the steady state sinusoidal material? Absolutely. For the in-class portion, I can't give you anything harder than I gave you on circuits 1 tests because you're restricted by the same shitty calculator. Yep.
So in the future, for this class, can we like the third or
Nope. Any class that you're taking with me will always have an in-class portion and a take-home portion so that I can restrict you to this kind of stuff and then ask you computer questions. The reason why I'm such an ass and keep making you just use these FE approved calculators is because at some point you're going to go take the FE and you need to know how to do that kind of material with this kind of calculator. I don't know if the 84s can, but I know I think like the 89s can, and there's a fancier one that came out after an 89 that I never wound up buying because I just stopped using even my 89.